I will talk to you about the time-resolved spectroscopies in a way answering part of the question that you asked before. I mean, the topic is very broad, so I started off with the definition of spectroscopy. And the broadest definition that I could find is that spectroscopy is the study of spectra. It's quite obvious. Namely, the distribution through a process that is called dispersion of a physical observable as a function of a continuously variable scalar parameter. And the word continuous is enclosed one of the biggest turning points of modern science, because the observation of discontinuities in emission spectra from the atoms is what had a very big part in the triggering the revolution of quantum mechanics. So this is very important. And let me also say that there is a very important germ, the germ of a very important concept also in the choice of scopy that comes from the Greek verb scopeo, which indicates observing with critical insight. And that creates the duality of spectroscopies, in which you have to look at spectra, but you have to be extremely critical in doing this. It's not spectrometry. You are not obviously quantifying something, but the difficulty is creating a quantitative measurement of something that is quite elusive. And the fact that it is elusive is also enclosed in the word spectrum that was introduced by Newton in the second half of the 1600s in his works on optics. And in that period, they were trying to disentangle the laws of optics, of geometrical optics, from the physiology of the observation of light. And therefore, they had a whole set of terminologies to define all the latent images in the eye that came from observing the speckles of light, of direct light. And so that's how the word spectrum was born. So because of this late Baroque and early Romantic origin of the spectrum, I put this background on the sleep of reason, because we always have to keep our reason awake, not to create monsters in spectroscopy. So let's get to a more precise definition. So it's the study of the interaction between matter and elementary particles, which are photons, electrons, and neutrons. It deals with the inelastic component of the particle-matter scattering process. And the continuously variable scalar parameter is the scattering energy. So the spectrum is given by the probability of the final states. So in a typical spectroscopy experiment, we have a primary beam, an object that for the next will be fundamentally condensed matter, and in particular solid state matter, but it can be also in the gas phase. And then we observe the three main processes that we can trigger by a primary beam, namely absorption, emission, and fragmentation. And this is mostly in the gas phase, the fragmentation. And then we disperse. When we look at the absorption, we generally scan the energy of the primary beam and observe an energy integrated quantity, that is the absorption, the transmission coefficient, or the absorption coefficient, or even the reflectivity. In emission, instead, we look, we use a monochromatic primary beam, and we look at the intrinsic spectrum of emission of particles from a material that is de-exciting the primary excitation. And finally, in the fragmentation, we look at the mass distribution of the fragments after the destruction of the object. So in creating a context from time-resolved spectroscopies, the next question is why performing a time-resolved spectroscopy? Well, the clear-cut answer is that going into the real-time domain, you can observe processes as they unfold. So you can disentangle the individual mechanism that drive a system that you set out of equilibrium back to equilibrium as it moves through the phase space. And the time-resolved spectroscopy have been done for a long time by the biophysics and chemical physics community, because they have much more complex phase space and that are spread over very large energy and time scales. So you can have protein folding or self-assembly of organic systems, or look at the kinetics of chemical reactions or diffusion processes. So these have very low energy scales, and therefore are spread over a very large amount of time scales. So for many processes, actually looking at processes in time was easier than separating them by energy, because these scales of energy are extremely small. On the other hand, for the condensed matter community, at long time scales, we have the domain wall motion in magnetic systems, or the ordering processes in liquids and gases, so that take longer time scales. So they were also time-resolved spectroscopy was performed on these materials. But as the technology of laser progressed and became very sharply timed emission of light became available on the scales of femtoseconds and picoseconds, then also the solid state community became interested in studying electronic processes that have much higher energies. And here, in this window, you can use time-resolved spectroscopy to disentangle which is the degree of freedom that orders condensed matter material, and that creates and that dictates the shape of the electronic structure of a material. In complex systems are extremely interesting because they have often a competition of ordered phases, and by exploiting this competition, you can create a very large response from a very small perturbation. But competition also means that you have that the energy scale of the ordered phase are very close between each other. And so it's very difficult to distinguish from equilibrium spectroscopy. But the interaction that are giving rise to an ordered phase can be of very different energy scales, and thus order the system on much different time scales. So you can distinguish on this scale. I will try to give an example later on this. So how do we trigger dynamical processes? Well, we need an excitation that must be extremely short, so it must be much shorter than the process that we want to look at, and it must be intense, so it must create really an out of equilibrium configuration in the system. So for the fastest process in condensed matter, it mostly can be achieved by high intensity laser pulses, optical laser pulses. For the excitation, there are three parameters that are relevant. So the time integrated power density, so how many photons per atom, after all, we are sending onto our sample. And so the important terms are power density, the volume power density, which is measured in millijoules per centimeter square, the fluence, that is the areal density of power, that is measured in millijoules per centimeter square, and the number of absorbed photons per atom, which can be calculated by the absorption coefficient. And look at these numbers. These are number of photons, absorbed photons per atom, that are extremely high. We are in the range. We are creating changes in a condensed matter system that are close to doping the system. So it's also sometimes it's also called photodoping. And then we have that is also very important, the pulse energy and the duration of the pulse, that together define the peak power that we reach. So because the de-excitation processes will start immediately after we have created the non-equilibrium configuration, as we we have to know what was the peak power that we sent on the sample, and thus how far from equilibrium we have set the sample. So in a very short time and with a very large number of photons per atom. And this can be in the gigawatt to terawatt range with shortly pulsed laser. And finally, for some studies, it can be extremely important to study to consider the wavelength of the excitation pulse. So we can have mainly two approaches to triggering dynamical processes. One is we are just interested to send the system out of equilibrium, and thus we are not very I mean, it's always relevant, but we are not extremely interested in the wavelength of the pump. And the other is instead to pump energy into a particular mode, into a particular excitation of the solid, and see how the solid reacts. And this, and for this, the wavelength is extremely important. So in how we do then, how do we observe dynamical processes? Well, I choose to put these three pictures to show the difference in an obvious way. So time resolution is a combination of the illumination that we use to probe the system and of the speed of the detector that we have. So we can, if we have continuous illumination and a slow detector, we are looking at the waterfall and seeing only stripes when at the water moving. So we are seeing either an equilibrium configuration or a steady state if we continuously excite the system. To observe, to freeze a dynamical process, we can use two approaches. Either a fast detector, so the time that is required to the detector to observe the process is shorter than the process itself, and we can use either continuous illumination or pulsed illumination and look at a long decay. This approach is limited by the characteristic time of the electronics of the detector, so it can go down to tens of picoseconds though, because technologies are very advanced in this direction. And on the other hand, we can have the approach of stroboscopic illumination, or of a sharp flash, in which we illuminate our material on a time scale that is much shorter than the process, and then we can take an exposure as long as we like, because then there will be just dark into the detector after the flash. So this is limited by the flash duration that, as Ricardo told you, can be extremely fast, down to attosecond time scales. So I wanted to show you an example of the fast detector method. The fast detector are the streak cameras. So they detect a spectrum that has already been dispersed in energy along one spatial direction, and then they disperse the spectrum also in time. So we send the light through an entrance slit that the light has already been dispersed in energy, and then there are some entrance optics. Then there is a photocathode, which is a metal with a very low work function, so even optical and infrared photons are able to extract electrons from it. Then electrons are accelerated by an acceleration grid, and then they enter to the most relevant element of a streak camera, which is a pair of plates in which a very sharp voltage ramp is sent through. So as the electrons enter the plates at different times, they are deviated by a different amount. Then the electrons are collected by a couple of a microchannel plate and a phosphor screen and a CCD camera. In this way, you keep the distribution along the horizontal direction of the energy, and you add the distribution along the vertical direction in time. And as an example, I wanted to show the photoluminescence of tungsten diselenide, which is a semiconductor that has a complex landscape of conduction band valleys. So when you excite it with a pulse of light, you create a number of different excitons into the material. And these excitons have different decay times depending on their characteristics and symmetry. So as you can see, the neutral direct exciton decays the fastest, and it's actually below the limit of detection of the streak camera, so it's 4 picosecond, and you can actually basically just see the laser pulse. Then you have a trion, which is a charged exciton that decays on 2 different time scales, on a longer time scale, and then you have localized excitons that take longest times. The other approach, the stroboscopic or flash method, looks only at reproducible configurations. So it consists in exciting the system, taking a snapshot of it with a flash at a precisely controlled, a precisely time-tagged delay. And we use a sharp flash, so we observe the process in a very precise moment. So we obtained a time-ordered sequence of frozen images in which we see the system out of equilibrium. And this was the first application of a stroboscopic method to see if the gallop of a horse was by keeping the hooves on the ground or not at all times. So this is implemented in what is called the pump probe method. So we have a pump that is an infrared pulse that is very sharp and that sends the system out of equilibrium. And then we send at a controlled delay a probe pulse that is used to measure the spectrum, the spectrum of the material, to see it in a precise moment at a precise delay after the pump in the out of equilibrium configuration. So the time between the excitation and the probe, then we re-prepare the system by exciting it again, and we change the delay at which we observed it. So again, we obtain a time-ordered sequence of the non-equilibrium state of the system frozen in time. Because we can acquire a measurement for as long as we like by staying at this precise delay. We can use low-intensity probe, so we can work. We can perform spectroscopy with a rather simple, in a rather simple way. As we will see, if we use single-shot approaches, will come in a minute, then you will have to use very high intensities, and you will be out of the approximation that your probe is just looking at the system. But if you use very high intensity, the probe will be also perturbing the system significantly. So that makes spectroscopy much more complicated. So here, the time resolution is given by the pulse duration and the timing accuracy. So how can we realize a very precise timing accuracy? So how can we control the delay between the pump and the probe? We use optical delay line that should have been here, but apparently it doesn't show up. Because the speed of light is very high, if we just send the light through a detour, so a U-shape inversion, and we control the length of the vertical braces of the U, then we can produce a delay between the pump and the probe beam. One of the beam goes through the U and the other one doesn't. And control it with a very high accuracy, because the light is fast. A difference of 1 femtosecond is a very manageable change in distance of 300 microns. So if we have a precise translational stage, we can achieve accuracy in the timing of femtoseconds or so. Then I wanted to show you also the single-shot approach. The stroboscopic method, as I described it, the pump probe method, again, probes only the reproducible paths through the through the phase space of a system. But what if we send a system into a metastable phase by optical excitation? Or what if we want to look at all possible paths that the system takes? Well, then we have to use single-shot approaches. But in this condition, then we need the intensity of the probe pulse to be enough to have a statistically significant measurement of the spectrum with a single shot. And then therefore we need high probe fluencies. So we challenge the fundamental assumption of a small perturbation of the initial state. So the two approaches are the dual echelon geometry, in which by making a flat pulse front cross wedged shaped optics, we create a two-dimensional set of delays. So for each pixel of the camera, we have a different delay. And then if we, in a single shot, we acquire all delays. So we pump the system and we look at all delays spread on the camera. So this is useful for large non-renewable targets and makes spectroscopy feasible because it uses relatively low intensity pulses, and it can map non-reproducible states, such as sending the system into a metastable phase. On the other hand, for the single shot, we have the probe and destroy approach, in which we excite the system and then at a control delay we send a pulse that is intense enough to look at the system, but also intense enough to destroy the system and short enough to see the system before it's destroyed. So this requires small and renewable targets and makes spectroscopy very difficult because, once again, the probe pulse perturbs significantly the state of the system. It's mostly used for diffraction and imaging of small objects. So then I wanted to draw a short, wide range map of the time-resolved spectroscopies. So if we look at the probe primary particle, how does time-resolved spectroscopy set with respect to the different particles that we can use? We know that we have at our veil neutrons that are massive particles, so they are very heavy, so they have short wavelengths, so they can look at very small energy excitations in matter, and they do not interact with charge, so they kind of draw a picture that is complementary to the one that we can see with electrons and photons. But for the case of neutrons, the limit is the generation of very short pulses, because that's what we always have to do to make time-resolved spectroscopy. So the generation process that are fission, spallation, and possibly laser-ignited fusion. Fission is very long and spallation is short, but on timescales of picoseconds. And laser-ignited fusion can be very short on femtosecond because, once again, it's triggered by a femtosecond laser. But then we have the fact that we have to moderate the neutrons to have the energy that we want. And this is a stochastic process that creates an uncontrollable broadening up to microseconds. So that makes it very difficult to make sharp pulses of low energy neutrons. And then we have also a strong time-of-flight dispersion due to the fact that they have mass. So they have a quadratic dispersion in time when they fly through the neutron guides. So these neutrons are very difficult to employ in time-resolved techniques. What about electrons instead? Well, they can be generated on ultra-fast time scales. So if we, electrons are produced from cathodes, and you can illuminate the cathode with a laser, so you can create a sharp pulse. Or you can produce field emission from a needle by triggering it again with the laser. if we create high densities of electrons, then we have space charge effects because the electrons are, have a very low mass and very high charge in proportion. So they feel significantly the space charge effect in vacuums that changes the temporal resolution. And once again, they have mass, so they have time of flight dispersion. This time of flight dispersion can be compensated by strong acceleration or by using single electron pulses, but that makes for very long measurements. So because of this, it's mostly used in diffraction and imaging because you have to use very high energies, and then spectroscopies of solids are quite difficult with many kilo electron volts or even mega electron volts electrons. So the time-resolved spectroscopies are the rain of photon pulses, mostly. And photons have their nice things, I mean. So they are sensitive to charge, they have selection rules which can be played with, and they have very large cross-section in matter. So with optical photons, I wanted just to throw in a few names of spectroscopies that can be time-resolved. Once again, we have to look at mechanisms, even in the spectroscopy, that must be much faster than the probe duration. Otherwise, we are looking at a phenomenon, at the de-excitation process and not at a spectroscopy. Once again, we lose the time resolution. So if we have a primary beam of optical photons, we can look at the transmission, the absorption, and the reflection of photons all the way through the spectrum of optical photons. We can look at the rotation of the polarization of the photons, which is a very important spectroscopy, Faraday and Kerr, depending if it's in transmission or reflection. And then we can look at the emission of terahertz radiation of the second harmonics at the interface, at Raman spectroscopy. Luminescence is kind of borderline because, once again, it takes a long time to decay. So there are some luminescence processes that can be used for time-resolved spectroscopy, and some others are the object of for example, the experiments with the streak camera. If we use high-energy photons, we are exciting higher energy processes, and we have a much wider map of possible spectroscopy that we can do. So we can look at the absorption with time-resolved X-ray, near-edge X-ray absorption spectroscopy, or extended fine structure spectroscopy. There are some very neat spectroscopy techniques that can be done, for example, in Grenoble, in the beamline of Sakura Pascarelli for time-resolved extended absorption. And then we can look at the emission of electrons in the Auger emission spectroscopy, in the fluorescence spectroscopy, and the photoelectron spectroscopy. Or we can look at the emission of photons in the resonant X-ray spectroscopy, X-ray Raman, and inelastic X-ray scattering. And we can also look, once again, in the gas phase at the fragmentation with coincidence mass spectroscopy. I will focus the next part of my talk on photoelectron spectroscopy. I don't know how familiar you are with photoelectron spectroscopy, so I'll go quickly through a primer on it. So X-rays in the range of the VUV up to tens of kilo electron volts have the largest cross-section of absorption into atoms with the photoelectric effect. So photoemission occurs when incident X-rays have sufficient energy to excite an electron into the continuum of unbound states, so into the free space. And the atom is left in an excited state with an empty electronic level which is called the core hole. And the remaining, the energy that has not been used to extract the electron from the atom is then given as kinetic energy to the outgoing electron. So you excite the system with a monochromatic photon beam, and the resolution of your technique depends also on the resolution with which you can say that your beam is monochromatic. And then you collect the emitted electrons and you disperse them by electrostatic methods as a function of their kinetic energy. And you look at their distribution, the amount of electrons that you get for each energy. Photoelectron spectroscopy is a final state spectroscopy. We must keep this in mind because we will need it for the example that I will use it later. So we must remember that we leave the atom ionized. So we will see, in part, the mechanism with which the atom screens the core hole charge that we have created. We will see them in the spectrum. If this was too easy, I put one slide that Chuck Fadley likes to show that shows in one single shot all the possible ways in which you can do photoelectron spectroscopy, adding spin resolution, to collecting different spins of electrons, using the excitation in total reflection or standing wave. You can go to high photon energies, you can go to high pressures because it's generally done in ultra-high vacuum. You can add space and time resolution, that's what we will focus on. And you can look at the distribution of electrons in the reciprocal space by looking at photoelectron diffraction. Obviously, this is the more vanilla version in which you look just at the core levels. And, or you can look at the distribution in momentum of the electrons in the valence band by performing angularly resolved photoelectron spectroscopy. What are the sources that we can use to perform photoelectron spectroscopy? We need sources of pulsed X-ray photons. So the amount of pulses of sources is limited. So we have the free electron lasers, which will be described in a talk by Claudio Masciovecchio. These kind of sources have a very high photon flux, the average photon flux, that is achieved, though, by a very low repetition rate and a very high amount of photons per pulse in short pulses. So we will see that this is not the easiest way to deliver light for photo emission. Then you can use synchrotron. They have fluxes up to 10 to the 14 photons per second, so lower than this, but they do it with a very high repetition rate, up to 500 megahertz. It's complex to synchronize a synchrotron with with a laser, they have generally long pulse durations because the duration of the pulse is set by the length of the bunch of electrons that is turning into the synchrotron. And we have a very small pulse energy. There is one way to achieve high temporal resolution with a synchrotron, that is femtoslicing. So you send in a laser that selects only one part of the bunch, very narrow. So you can achieve hundreds of femtoseconds, but you have extremely low fluxes because you are bound by the repetition rate of the laser, so you can use only few bunches of the synchrotron and only a part of the bunch. So you are throwing away an enormous amount of photons. And then there is laser high harmonics generation that Riccardo just explained to you. It can reach high photon fluxes, and we will see that this is kind of the limit photon flux to perform reliably time-resolved photoelectron spectroscopy. It has a medium to high repetition rate in the kilohertz range, and it's obviously synchronized because you produce the UV by the same laser that you use to pump. And then you can have very short pulse duration. obviously in choosing the pulse duration, you can tune it quite easily in high harmonics. You have to keep in mind the time bandwidth limit. So if you squeeze the pulse too short, then you will need a broader spectrum of the pulse to do it, and vice versa. So we settled in our laboratory to around 300 femtoseconds so as to generate very high resolution for photoelectron spectroscopy, which is needed. What happens when you produce the emission of photoelectrons with very sharp pulses? Well, the electrons feel the fact that they are being generated at the surface of the material in a small spot all at the same time. So you create a high density of charge, and electrons start interacting between each other. And we have the simplest case, that is space charge effect within the probe cloud. So we excite the system with a probe, and we look at the electrons, and the electrons are repelling between each other. And if you look at this spectrum with increasing excitation density of power of the probe, you see that it really is destroyed completely. So this is a problem in photoelectron spectroscopy, and we have to cope with that. This is a problem in choosing the source for photoelectron spectroscopy. But there is another problem, that is that also the pump pulse can produce electrons. We are exciting the system with a large number of photons that individually are not able to send the electron out of the solid because they are below the work function of the solid. But if we create multi-photon absorption, so we make the electron absorb several photons at once, then we can excite the electron out of the solid too, and create another disk of electronic charge at the surface of the system. So if we excite with too large photon densities, then we create a cloud from the pump and a cloud from the probe, and we have shifts that are changing as a function of the delay of the photoelectric spectrum. So this is difficult to deal with. So the strategy, the simplest strategy to perform photoelectron spectroscopy is to go to high repetition rates and lower the power density of both the pump and the probe pulse. And here I show this image in which I have normalized the I have normalized to the maximum amount of photons that you can use before producing space charge in your spectra, which is 10 to the 6 photons per pulse. So if we reduce the amount of photons per pulse that you can use in a free electron laser that has a very low repetition rate, then you get photon fluxes that are very low, usable photon fluxes that are very low. So you are dealing with bad statistics in your measurement. On the other hand, you have also a limit on the maximum repetition rate, because if you go too fast, then the sample doesn't have time to recover the equilibrium state. So it's possible to fix somehow a limit of the maximum usable photon flux of the time resolved photoelectron spectroscopy that is in the 10 to the 12 photons per second. Does it ring a bell? Is what we have in our high harmonics generation laboratory. So we are here in the soft X-ray range, and with high repetition rate and just the right amount of photons per pulse. On the other hand, if you need higher photon energies, then you have to realize high repetition rate free electron lasers, which are still underway, or to use synchrotron radiation accepting a reduced time resolution. So let me go through the examples. I don't have much time, so buckle up. I will try to do something to show. So we studied one sample that is a magnetic oxide it is ferromagnetic, and the movement of charges into the material is obtained by a double exchange mechanism in which electrons hop through the ions in the crystal only if the magnetic moment of the manganese ions are aligned. And this couples strongly the transport and the magnetic order and creates a structure of the electronic structure close to the Fermi energy that is exotic. It's half metallic, so meaning that the material is a metal for one spin state, but a semiconductor or an insulator for the other spin state. So we have a virtually very high spin polarization at the Fermi energy, and peculiar magnetic properties. So let's go back to the picture that I showed you in the beginning of the different sets of excitation process that we can trigger. In a magnetic material such as this, we have 3 sets of possible excitation that we can trigger by exciting with a short laser pulse. So let's start with a simple ferromagnetic metal. We excite with these systems are the charge, the kinetic energy of the charges, the vibration of the lattice, and the order of the spin, the magnetic order. So if we excite the kinetic energy of the electrons, then we produce optical vertical transition, and we increase suddenly the temperature of the electrons. Then the electrons are strongly coupled with the spins through the spin flip scattering processes. So they have a way to relax the energy into the magnetic order that is very fast. So the temperature of the spin system will follow closely the one of the electrons, and then they will both quench their energy into the lattice, which has a much larger heat capacity and thus heats up slowly to reach an equilibrium configuration. In a half metal, because we do not have spin minority state at the Fermi energy, we cannot do the spin flip scattering that relaxes the energy from the electrons into the spin order. So the system will have first to warm up the lattice and only very slowly heat up the magnetic order. So the collapse of magnetic order is extremely slow with respect to metals, and in LSMO takes time scales longer than 200 picoseconds. But what happens to the electronic structure? We said that the electronic structure is strongly coupled to magnetic order. Does the fact that the magnetic order is the one that is driving the movement of electrons through the crystal keep the system metallic on long time scale, or the system becomes insulating and demagnetizes later? Well, that's what we try to look at with time-resolved photoelectron spectroscopy. Now there is a big problem with performing photoelectron spectroscopy with oxides. They tend to have significantly different properties at the surface. So you need to look into the bulk. And to do that with photoelectron spectroscopy, you need to increase the photon energy, and thus the energy of the photoemitted electrons, and let them exit from a larger portion of your solid without losing the energy information. This comes at a price, though, because the cross-section, the photoelectric cross-section, decreases significantly as you increase the photon energy, and therefore you become less and less able to measure clearly, and you have less and less statistics, basically. And this decreases particularly fast for the valence electrons that are the ones that we want to look at. So we need to find a fingerprint of how the electrons are mobile through the crystal by looking at the core levels, which are easier to measure. And luckily, this is possible. So you can look at the satellites of the core level peaks, and if you increase the photon energy and you reach the region which is metallic, then you see appearing a satellite in the manganese 2p peak that shows that arises from the fact that electrons in the bulk are able to move more freely and thus are able to screen the core charge that we created by ionizing. And so this new mechanism for screening the charge appears only in the bulk, and thus we see a new satellite appearing when we increase the photon energy. This peak also shows a significant contrast when we measure it with circular polarization and opposite magnetization. So by using the selection rules, we can say that it is magnetic. It is sensitive to magnetism too, and also changes shape as we cross the Curie temperature of the material. So we have a confirmation that this is a fingerprint of the mobility of the electrons and the magnetic state of the system. How can we do, though, time-resolved photoelectron spectroscopy with hard X-rays, because we are using 6 kiloelectron volts or 8 kiloelectron volts? Well, there is basically only one place in the world that does it. It's beamline at Spring 8. So they use the pulses of the synchrotron that come at 40 megahertz and 8 kiloelectron volt. They have a duration of 40 picoseconds. And then they chop them down to match the repetition rate of the laser. And then they shine the laser, the pump laser, and they control the delay between the synchrotron pulse and the laser pulse. And if you do this on the manganese peak that I showed you before, you obtain this cascade. This is a measurement of the peak with the laser, the pump laser switched off, so that we look at the equilibrium state. Then we look at negative delay, meaning that the probe is arriving before the pump, and this is equal. The shape of the peak is identical to the one of laser off, and that allows us to say that we are not creating permanent changes by shining the laser. And then at the shortest delay, we see that this satellite is quenched, and that and then when the sample cools down, the peak recovers. So how can we interpret this data? Well, we can look at the difference at two different temperatures at the equilibrium. So these are static measurements at two different temperatures. We see that the spectral weight is changing here, but it's changing also here. So we see that the peak decreases here, but we have also a change in this part. If we look at the shortest delay, we see that we have a decrease here, but no significant change in this part. So this is a non-equilibrium line shape of the peak that is measured with a 40 picosecond pulse. That means that the electronic structure is staying out of equilibrium for very long times. And on the second, and if we go at longer delays, we see that instead the variation of the line shape is much more similar to the one of equilibrium variations of the temperature. So we can look at the collapse of hybridization, and we can say that it takes extremely long times. So that is controlled by the time scale of the magnetic relaxation. So we can answer that question, that if magnetization kept the system active and metallic, and that's yes. And also we have hints of the fact that we have substructure dynamics. So let me just show you very briefly, it would need a longer explanation, but very briefly, another example of how it's possible to use time-resolved spectroscopy to distinguish between different mechanisms driving the order in the electronic structure. There are different types of mechanisms that can make a system an insulator non-trivial. One is Mott localization that arises from the fact that the bands in which the electrons are moving are narrow, and there is a large electrical repulsion between the electrons. So that is a charge to charge interaction. Then there can be localization due to excitons, in which the excitons are created and localize the charges in indirect gaps. And then there can be a Peierls effect, meaning that we create a lattice phase transition that rearranges the unit cell and creates gaps at the boundaries of the Brillouin zone. And all these interactions have different energy scales and thus different time scales, although at the equilibrium, if we look at the ordered phases that we can create due to these different ordering mechanisms, they can be all present at once, because there is always some electron-electron interaction, always some electron-lattice interaction, and always some screening due to excitons. So it's very difficult to disentangle, but if you look at inside the gap in different classes of materials, in particular this study was done on quasi two-dimensional transition metal dechalcogenides, you can really recognize what is the interaction that is driving by the time scale that in which you observe the collapse of the gap. So the gap disappears, we see some photoemission intensity in the gap. That means that there are carriers at the Fermi energy. And at the gamma point in tantalum diselenide, we have a well-acknowledged Mott transition. And if we look at the time scale, it takes less than 20 femtoseconds, which is comparable with the time scale of the hopping of electrons through the crystal, really. That is on the scale of a few femtoseconds. So this can be recognized as a Mott transition. In the very same material, at the boundaries of the Brillouin zone, you can also see the concurrent Peierls transition and disentangle it by time scale. So at the endpoint, you can see that there is the intensity scales much more slowly. And this is because it is required a change in the crystal lattice. So it takes half of the time of the phonon that is moving the atoms from one place to the other. And this is exactly 206 femtoseconds, and the time scale is very close also here. But this can also be used to recognize the time scale in different complex material in which is not obvious. In tantalum diselenide, it is known that is a concurrent Mott and Peierls transition, but for example, in tantalum diselenide, it is suspected that is an excitonic process, and indeed you see that is some process that is between the timescale of electron-electron interaction, and it's longer than electron-electron interaction, direct repulsion between the carriers, and it's shorter than a lattice rearrangement. So it has the time scales of screening close to the plasma frequency, and therefore it's labeled as an excitonic transition. And on the other hand, in a material that was not known to have a Peierls transition, it was demonstrated that this is a lattice-driven metal insulator transition. So with this, I point out the take-home messages that I wanted to deliver. It's the fact that spectroscopy in the real-time domain follows the formation or collapse of equilibrium and disentangles the mechanism, allows you one more tool to disentangle the mechanisms. And that you have many spectroscopic techniques that can be time-resolved, but you have to take care that the elementary process is fast enough. And finally, achieving time resolution must be done with very, once again, with reason, by thinking, because this may challenge the very foundations of the technique, as we said. And with this, I thank you for your attention. And I also want to thank the awesome team I work with, which is the NFFA group in Trieste. And these are the facilities that we have available. One of these is the Sprint laboratory. And they told me to mention that we are hiring.